And welcome to today's Science in Schools webinar. My name is Nick Muldow and I am the Outreach Manager here at the UK Atomic Energy Authority, where we have the hottest place on Earth. And I'm going to tell you all about that in the next hour. If you've got any questions at all and are listening to us live, do feel free to put anything you would like into the chat box. We may be able to pick up some of them as we go along, but there will be some time towards the end to really get stuck into any questions that any of you might have for us today. Just to tell you a little bit about Science in Schools before we get properly started, this is a non-profit magazine actually funded by a European collaboration of major government research organizations all across Europe. So that's why we have a lot of people from all over Europe calling in today, which is fantastic to see. And this magazine is really great. It can be for teachers, it can be for students, anyone that is interested in loads of different topics of science. They put out these monthly magazines with loads of different really cool and interesting topics in them. And they have recently started this new webinar series, which is what we're going to be doing today. The next webinar, if any of you are interested, is going to be on February 24th, and it's all about exoplanets. So do check out and have a think about tuning in for that one. But moving away from space and much more to some cutting edge technology that's going to be happening here on Earth. So in the next 45 minutes or so, I am going to show you around the hottest place on Earth and really explain to you what that really means for all of our lives in the future as well. Because in fact, at the UK Atomic Energy Authority, in collaboration with scientists from all over Europe, with a program called EUROfusion, we are researching a technology known as fusion energy. And we believe that fusion is going to be really important in the future of all of our lives as a new energy source that will provide us with low carbon, sustainable energy into the future. And we all know how important that is. But before we get stuck into fusion, I just want to give a little bit of background. So we're all very much aware that we need more sustainable energy sources. Climate change is a big issue. The world is heating up, and with that, there's causing lots of change to habitats all over the world for humans, for animals, for plants, and all sorts of other species too. And if we are going to keep on having the biodiversity that we have, keep on living the nice lives, technological lives that we have as humans, we are going to need to take better care of our planet. And one of the things that we need to do that is have more sustainable energy. And we can't rely on fossil fuels much longer. So we all know that fossil fuels are bad for the environment because they cause greenhouse gases, which cause climate change. But this stuff also doesn't last forever. We have to dig up fossil fuels from the ground. And at one point, there's going to come a time when there aren't any more fossil fuels left for us to use. And so even if climate change wasn't an issue, we'd be facing an energy crisis in not too long. So we really, really need to be thinking about getting new energy sources and ones that are sustainable for our planet. And this is where we come to something that we call the energy mix. Now, what does this mean? Well, this is basically just talking about all of the different types of energy that we use to produce our electricity and our power. You can see here on this graph that in the middle, we're sort of just past 2015, a few years on from that now, but it's still showing that a large amount of our energy is coming from fossil fuels. And even going into the sort of near future, it's predicted that fossil fuels will still be a large part, but we're going to start increasing other technologies and get away from fossil fuels. We all know that we need to get rid of this part of the energy mix. With this, we're looking to expand technologies like renewable energy sources, such as wind power, solar panels, tidal. All of these are really good because they're producing clean energy, not causing greenhouse gases or climate change. And we also are looking to develop the current nuclear technology that we have in the form of fission. And this is what happens when you take very large, heavy atoms and split them up to get energy. And that doesn't cause climate change either. However, both of these groups of technologies do have their downfalls. Renewables have to rely on natural resources. And so therefore, they're not going to work all the time. It's not always windy and it's not always sunny. So we're going to need other sources as well. And with nuclear fission, this produces quite a large amount of radioactive waste that will last radioactive for many, many years. And so that itself is a bit of a drawback too. And this is why we still feel that while these technologies are really, really good in the short and medium term, in the long term, we're going to need something new that we don't have just yet powering our energy sources. And this is where we think that this big gap that's going to need to be replaced by fossil fuels will be replaced with this fusion energy technology and will provide what we call baseload power. This means that we believe in the future, fusion will provide the majority of energy that countries all over the world will actually be using, but there'll still be a role for other technologies like renewables to help top up all of that energy to meet any demand when we get really, really high power needs. So, what is fusion? I wonder, what do any of you know about fusion? Do feel free to put anything in the chat box as we go along. But what we're going to do for the next 10 minutes or so is just take you through some of the basics of what fusion actually is. Now, first off, you need to know that nuclear fusion is a natural energy source. It's one of the most abundant in the universe, in fact, because it is the power source of stars like our own sun. Right in the core of the sun, you have lots and lots of fusion reactions happening every second. How does that work though? Well, to understand fusion, I feel the best place to start is with something really, really quite small and basic, the atom itself. So fusion is a nuclear energy source. And all that means is that the nucleus of an atom, this central bit right in the middle here, made up of the protons and neutrons, this changes when you combine small light atoms together. So what we have here is two small light atoms fusing together to make a bigger atom. And every time that happens, we get this release of fusion energy as a result. And this reaction will happen millions and millions, if not billions or more, every second inside, not just our sun, but all stars out there in the universe. How does fusion happen inside stars? I mean, on the face of it, that reaction looks very, very simple, but it can be very challenging to get the right conditions needed to force those atoms together to make them fuse. One of the first things we need to think about is getting our atoms into the right state of matter. So we'll all know about solids, liquids, and gases, but did you know that actually when you can superheat a gas and turn it into a fourth state of matter known as plasma? Now, in solids and liquid gas, all of the atoms are contained and kept together with the nucleus in the center and the electrons whizzing around the outside. But when you turn it into a plasma, those electron particles and the nucleus start to separate, and you get this disassociated soup of plasma. And actually, plasma itself is charged because the nucleus of atoms are positive and the electrons are negative. And that will come in really useful when we talk about how we're trying to recreate this fusion process right here on Earth. So first condition is that we need plasma. Then we also need a fuel. Now, not all elements can fuse, but the most basic element, hydrogen, is a really good fuel for fusion. It's the main fuel that our sun uses. And when you fuse two atoms of hydrogen together, you actually create the next element up, which is helium. So we need some fuel, but we also need some really extreme conditions, including really high temperatures. Now, inside the core of the sun, we get up to 15 million degrees. That's really, really quite hot. We also need very high densities. So this is where all the atoms get packed in really close and tight with each other. Inside the sun, you get up to 150 times the density of atoms in water. And together, these two features give us extreme pressures, up to 250 billion bar in the core of the sun. Now, for those of you that might not know, 1 bar is 1 atmosphere of pressure that you might feel if you were to just step outside your house into the fresh air. The highest pressure anywhere on Earth is in our own planet core of 3.5 million bar. Very, very extreme for us. Wouldn't want to be in the center of there without any protection. But it's still billion times more the pressure inside the core of the sun than in our planet's core. So this just really shows you how extreme the conditions are inside stars like our sun. And it's only with these extreme conditions that we can actually make fusion happen. Because what we have to do is overcome some very basic forces. The main one being this, the electrostatic force of repulsion. Now, if you remember, when atoms are in that plasma, we said that they're charged. And what we're trying to actually do is force the nuclei of those atoms together. Now, those nuclei are positively charged. So naturally, two positives would want to push away from each other, just like the same ends of a magnet. But to help overcome this electrostatic force of repulsion, this is where we add in our extreme conditions of high temperature, high densities, and high pressures. And when you apply all of those, you can actually overcome that repulsion and force the atoms to combine, force nuclei to fuse together and release out this fusion energy. So that's how it happens inside the sun. Why would we be interested in bringing that technology down to Earth? What could fusion do for all of us? Well, it has many advantages over some technologies that we have right now if we were able to really power our grid. Firstly, it produces a carbon-free reaction. So the reaction to make fusion happen, we'll go more into it in a moment, is just fusing those hydrogen together to create helium. And with our product, with our reaction, we also produce an extra neutron. But there's no carbon dioxide or other greenhouse gases being produced. So good for the environment. We could also have a continuous power supply. We wouldn't have to depend on whether it's sunny or windy. We could just switch on a future fusion power plant and be able to run it whenever we would like. It also is better than nuclear fission technology because it produces much less radioactive waste. And the radioactive waste is also radioactive for a much less amount of time. Yes, we do produce some, so it's not completely perfect, but it is a lot better than anything that we have at the moment. It's very, very safe too. If you imagine trying to recreate all of those conditions, you might think that it's quite dangerous to play with really high temperatures. But as I'll explain to you, we have a really good way of containing all of the high conditions that you need for fusion to happen here on Earth really safely. And if any of the conditions are not met and are not kept really constant, then actually the machines we have completely switch off and there's no chance of any runaway reactions and meltdowns. So we've got really, really nice, safe technology, and we really care about safety when we're developing all of this as well. And there's lots and lots of fuel for us. So the hydrogen that we use, we can actually get from seawater. And there's also some other ways that we're looking at getting our hydrogen too. And we don't need very much of it for fusion, because a small amount of hydrogen that we use in the fusion machines we have can actually produce an enormous amount of energy. So rather than needing many, many tons of coal, we would only need a fraction of that much to produce the same amount of energy from the fuels we'll be using for fusion. So what we're trying to do is try and find a way to bring that technology from the sun right down here onto Earth and recreate this. The first thing that I want us to look at is actually the reaction itself. So we said that in the sun, we need plasma. So we're going to get our atoms into the plasma state. And what atoms are we using? Well, we've already said that we use hydrogen, but we use two special forms or isotopes known as tritium and deuterium. And these create a helium as a product and a very high energy neutron. So when our deuterium reacts with a tritium, we get a change in the nucleus, and we also get a release of an extra neutron, which is very key to ultimately how we're going to be trying to get the energy out of this reaction. The helium itself is actually somewhat of a waste product, because what we're trying to do is extract as much energy as we can to one day produce electricity. And that high energy neutron can give us lots and lots of electricity and power down the line with a technology that we're researching here and across the world in other fusion labs. So imagine trying to bottle up a star and putting it onto the garden of your house. Might be a bit tricky because stars are massive. We can actually use magnets to confine star-like plasmas. So if we would just have a hydrogen plasma bouncing around in a tube, it would go in all sorts of different directions. When we apply a magnetic field, because that plasma is charged, we can actually control the shape and direction of all of those plasma particles. And this is really, really neat for us, because it means that we can create the machines that we need using this technique called magnetic confinement. But we don't just want it in a tube, because otherwise it would go out the end. And so instead we curve our tube around and it turns it into what's effectively a donut. So this ring-shaped structure is the form that we have for our fusion machines. And it's proving really, really useful. And this is what brings me to the type of machine that we use to make fusion here. And this is known as the tokamak. Now it stands for toroidal chamber with magnetic confinement. That magnetic confinement bit you've already learned about as being what we use to control the plasma and the charged particles. The toroidal chamber means that donut-shaped vessel. So right in the center here is actually this pink cloud of plasma. Around the outside are the magnets that we use. We have two sets of magnets to confine our plasma. The first are these big blue D-shaped rings known as toroidal magnetic coils. And they help to create a magnetic field going round the torus, or the donut shape itself. And then we have another set of magnetic coils called the poloidal magnetic coils. I like to think of them as polos because they wrap around like a polo might. And they create a magnetic field going up and around the plasma that helps to squash that plasma within the machine itself. If you just take a look at the background of my virtual camera right now, this is a look inside JET. And you can see the metal-shaped ring matching up with the tokamak structure you've got inside there. Now, I'm going to tell you more about JET in just a moment. But before we do, just want to show you a couple more features of the tokamak. Right in the center of the tokamak, we actually have something known as a central solenoid transformer. Now, this central column acts like a transformer to create a current inside our plasma, which is this big cloud, pink cloud within the vessel being contained by the magnets. And this current is really, really useful for us in trying to meet one of the key conditions that are needed for fusion, which is that high temperature. And this is the bit that I'm going to talk about next, and this will be the last bit of the sort of basics of fusion that we need to understand the rest of the things we'll talk about in this webinar. And there are 3 heating systems that we actually have on JET, the tokamak here at UKAEA and in Culham Science Centre, Oxfordshire. The first is ohmic heating. And this relies on that central solenoid transformer. When you get a transformer, you can create a current within the plasma, and when you increase the current, you can increase resistance. And some of you will know that when you increase resistance in a system, you actually get an increase in temperature. And that increase in temperature is something that we can use, which is really, really good. But we also need more types of heating as well. Ohmic heating is not enough to get us to the really extreme conditions and temperatures that we need to make fusion here on Earth. We have this other one called radio frequency heating, which works a little bit like how a microwave might heat up your dinner. You fire in electromagnetic waves tuned at the right frequency to vibrate those tritium and deuterium plasma particles. And when they do vibrate more, they're getting more energy, and then as a result, getting more temperature within the system again. And then lastly, we have neutral beam injection heating. This is a really specialized type of heating where we fire in higher energy particles and we make them neutral. So they're not going to interact with the magnetic fields, because all we want interacting with the magnetic fields is the charged plasma itself. And when we fire in these neutral beam particles, they start to hit some of the plasma particles themselves, and thus transferring more of their energy again into the system and creating even more temperature. Taken together, these 3 heating systems allow us to get even hotter than the sun itself. In fact, tokamaks can get up to 10 times hotter than our sun. And this is what makes them not only the hottest place on Earth, but also the hottest place in our own galaxy too. So it really is quite impressive technology. And we have to get hotter than the sun, because the sun has all of those extra advantages of being really, really large with high gravity and creating that high pressure. Instead, we overcome this using the magnets and getting even hotter than some stars do. So to get from the tokamak to electricity in the future, we actually need some infrastructure around this as well. At the moment, we're at the stage of developing fusion, understanding how it works and how we can make it work even better. And this is the thing that we're really focused on, is creating these fusion power stations with a power source from fusion. But ultimately, we're going to need something that can generate electricity. And to do that, we'll have some way of heating up water, making steam, which will then turn a turbine and go to a generator, and then ultimately go on to the electric grid as a result. How are we going to get the energy out of our machine to heat up that water? Well, if we have a little look at our reaction again, and remind ourselves that tritium and deuterium fuse to create helium and a high energy neutron. And it's this high energy neutron that actually we're looking at developing a technology where that neutron will fire out of the tokamak and hit a metal layer made out of lithium. Now, this is what we're calling the lithium blanket, because the lithium metal will heat up because of its reaction with the high energy neutron. And the heat from that lithium can then be used to heat up the water and turn it into steam, and then ultimately go on that line down to the national grids, which is really, really good. But not only can the lithium blanket allow us to get energy out of the tokamak, we can also get more tritium using the lithium blanket too, because the reaction between a neutron and lithium actually creates more tritium as a result. So not only are we getting energy out of the system, we're also being able to create even more fuel using this technology too. So it really could be game changing when we get a lithium blanket technology working for our future fusion power stations. Now, what we're going to do next is really focus in on JET, the Joint European Torus. This is a machine that's been running since 1983 and has given scientists working in fusion lots and lots of data about how we can transform this technology into a way of making future fusion power stations. Now, you can see on the left here, a big cartoon structure of JET. Right in the center, you have the metal vessel where the plasma would be. The slacks that you can see sort of look like they might represent the toroidal magnets. And the orange rings going around the top and bottom, those are the poloidal magnets. So remember that magnetic confinement, really, really key to making fusion work in a tokamak. But you also have these big limbs that we call them. They're feeding into the central column that helps create that ohmic heating as one of the key heating systems. On the other picture here, we have a picture of the inside of JET. And you can see it's a really complex vessel and machine on the inside. It's got lots of metal tiles made up of materials called tungsten and beryllium that have really high melting points. So even though we get up to 150 million degrees, remember that's 10 times hotter than the sun, that only happens right in the very center of the machine. But still, by the time you get to the edges of the plasma cloud where it might touch the machine, you've still got high temperatures in the region of a few hundred to maybe 1,000 or two. And we need strong materials that can stand the heat coming from those parts. And then right on the far end over here, we have a picture of what it looks like with a plasma inside JET itself. You can see this faint pink glow of a plasma, which is the same picture that you've seen in my background. Now, what I'm going to talk you through is actually some of the people that are needed to operate this machine. And for this next part, what I'm going to try and do is just talk you through where JET is and then show you around one of the operational areas, which is actually where I am today. And I'm going to remove my virtual background and show you around one of the key spots that's needed to make JET really work. So at UKAEA, we are the operators of this fantastic fusion machine known as JET, or the Joint European Torus. And where can you find JET? Well, you can find it in Oxfordshire in the UK at a site called Culham Science Centre, just a little bit south of Oxford. And at this site, there's lots of science and engineering and technology going on. But fusion is one of the core pieces of work that goes on at our site. And this is what our site looks like from the air. You can see it's really quite pretty. Nice bit of countryside, and that big building that's sticking out in the middle, right there, that's just been highlighted, this is JET. It really is a mega structure. And there's lots of different pieces that need to come together to make JET work properly. So what are some of the areas that are needed? Well, there's two key areas that I'm going to talk about today. And the first one will be the JET control room. And this is where lots of staff at UKAEA work to make sure that the machine is running properly and gets all of the data that's needed to help push forward our knowledge of fusion. But the machine itself actually sits far away from the control room in an area known as the Torus Hall. And it's named that because the machine is a torus. It's that donut-shaped tokamak. So this is the part where I'm going to talk to you more about the control room itself, and I'm going to take away my background. So hello everyone, here I am inside the control room. So where I'm sitting right now is actually where lots of different staff work to make JET run all of its experiments. And we can run experiments every day on JET. In fact, when JET is running really, really well, we can run experiments every 20 minutes. So that you can imagine that there's lots and lots of data to be got from JET every day. Now I'm going to hold up the camera and try and show you and point out some of the people that are needed. And what you might hear sometimes in the background is a sound going off, and that might be when we actually run one of our experiments, which we call pulses. So let's keep our fingers crossed to try and maybe get a pulse happening at some point during this webinar. All right, I'm going to just hold up the camera now. And so hopefully you can now see over there is where there's lots of screens lit up with people standing up, some people sat down at computers, and this is one of the main teams that are needed to run and operate JET. The person that you can see standing up in the far corner just there, this is known as the engineer in charge. They have a really important role on JET to make sure that everyone stays safe, but also that the machine itself is kept safe. So the engineer in charge works with everyone in the control room to make sure that all of the experiments that are running are going to run as they're needed. And when the engineer in charge is happy with everything, they say, okay, good to go, and we can run our next experiment or our next JET pulse. Also around the engineer in charge, we've got other people like a diagnostic coordinator, and they monitor all of the data and results coming out from the many different diagnostics on JET. There's over 100 different diagnostics that are needed to make us understand lots more about fusion. Far away, past that glass wall, that is where we have whole teams of engineers, and they will be running things like the heating systems, whether that's the ohmic heating, the radio frequency heating, or the neutral beam system. And there's also groups that control the power to the magnets too. And then if we just zoom around the rest of the room, right now you can see there's a lot of empty chairs in this space. And actually, in normal times, this would be where we have lots of scientists come to visit from all over Europe. Now, right now, we're doing a lot of our work still on Zoom and connecting with scientists around the world remotely. But when things are more normal again, we can bring all the scientists back into our control room, and they can work directly with the engineers in charge and with the scientific coordinators and all the other key roles that are needed to really make JET come to life every time. And this is also why I have to be in a face mask today, because inside the control room, we're trying to be really, really, really COVID safe and COVID secure, making sure that there aren't that many people in here, making sure that we've all been tested regularly, and making sure that all of the work that we really want to get happening on JET keeps on running as much as we possibly can. So hopefully this was quite a nice little bit that not everyone normally gets to see. It's very rare even for myself to be found in the control room. So it's certainly exciting for me, and I hope it's been exciting for all of you to have a little sneak peek at some of the behind the scenes work that's needed to run JET. I'm going to bring up again the PowerPoint and talk you through some of the other bits of JET And we said that there are different roles needed inside the control room. So here's just another view of the control room from the back, and you can still see that main desk over here, where if we were running experiments, there'd be lots of data coming off the screens all the time. And this is what it looks like when there's lots of people all gathered around when a pulse is going off. You get live data, including live videos of camera views inside the machine itself too. And just on this bottom map, you can see that there's lots of different roles. I mentioned some of them. The EIC, that's the engineer in charge. The DC, that was the diagnostic coordinator. And the SC, that's the scientific coordinator who works with all of the visiting scientists at different labs. So you can see there's a lot of people that are needed to make JET run smoothly. Now, moving on from the control room, I want us to have a little look inside the Torus hall itself and try to get a picture of what JET looks like from the outside. So if you were to go in the Torus hall, you'd actually come into this big warehouse room past these massive walls. And actually, what looks like a wall to the side there is a huge door. It's about 3 meters thick. And that's there to help make sure that everyone else is kept safe, because those high energy neutrons that come out, if a neutron was to hit someone like you or me, it wouldn't be very good. But if we keep it contained within the Torus hall itself, everything is all good and safe. And this is what JET really looks like from the outside, from an aerial view. You can see just how much technology and equipment is really needed to make it work. You've got lots of different diagnostics that have been added to JET over the years. I mentioned that there's over 100 of them now. This big tower with many ports that are going into the machine in the corner on the sort of bottom left, that's one of the neutral beam towers that are firing in those neutral particles to heat up the plasma. These orange bits that are sticking out that you can see dotted around, those are the limbs that you saw in the cartoon before that help to feed in to the central column and creating that current and giving us ohmic heating. The vessel itself is actually only a fraction of this machine right in the center. You can see just how high or how tall this machine is by having a look at some of the stairs down there. It's about 4 or 5 stories. It's 12 meters high as a machine. JET really is a huge device and also a really powerful experimental machine for all of us to use. So, going on from the Torus hall, just another little look again at the vessel. You can see all of that technology that was needed from the outside is all there to just make sure that what's happening inside the vessel is happening as good as it can. And all of these people behind me are working hard to try and make plasmas that can give us lots of data so we know how to build the best fusion machines in the future to build our power stations from them. Now, I'm going to try and keep an ear out for any pulses that might happen today while I sat here. And if there are, I will switch live to some of the pulses that might be happening in the control room. But while we do that, we'll push on and just tell you a little bit more about some of the other fusion projects that are going to be needed to get us from JET and the experiments to full fusion power stations in the future. Now, 2 of the key European projects, and in fact, even more international than that, are machines called ITER and DEMO. ITER is the International Tokamak Experimental Reactor, and it really is international. It's got 7 major partners and many, many more minor partners. So Europe is all contributing. There is America, Russia, India, China, Japan, and Korea. And these are all the major partners which represent over half of the world's population. And it really just shows you how much commitment there is now in fusion. And all of these countries are working together on one single machine to try and further everyone's knowledge of fusion, so that if we can all contribute to build a really big machine, that machine may be able to produce enough power for us to be able to prove that fusion really can be made at a commercial scale, at full-scale power plants, which is our ultimate goal. And all of the technology that's coming away from ITER will help feed it back into all of these nations and help all of us build more fusion machines in the future. Then we have next project called DEMO, and this will be the main European-wide prototype fusion power plant. And this will be taking the same technology, that tokamak technology from JET and ITER, and scaling it up even more to build a full power plant site that will hopefully even have a connection to the grid and may even be able to power some homes. And once we've got one of these prototype power plants, then we'll have a blueprint to be able to roll it out all over the world. But the conventional tokamak that JET, ITER, and DEMO are on is not the only way that we could get to fusion power. At UKAA in Oxfordshire, we're also looking at another technology with two machines called Mast Upgrade and STEP. Now, Mast Upgrade is still a tokamak, but this time it's much more squashed down, it's more compact, and it's got a slightly different shape called a spherical tokamak instead. Now, because of all of those things, it may be that we can create a more efficient, more stable plasma. And then we could run our pulses and our fusion power more consistently with these machines. And also, if we had many small fusion machines on one power plant site, rather than just a couple, like 2 or 3 big conventional tokamaks, with the smaller ones, we could be more agile and more flexible. So we could have maybe a few tokamaks switched on at a time if there wasn't a lot of demand needed. Or we could switch all of them on, or we could switch 60% or 30%. It all completely means that we can just have much more flexibility within our power system using that technology. Now, STEP is taking our machine of Mast Upgrade that we have built right now and are even operating at the moment, taking that technology even further to make a prototype spherical tokamak. So this is a parallel to DEMO, but STEP will actually be made in the UK somewhere. And right now we're going through the process of finding a site in the UK to place STEP. And we're hoping that STEP is going to be built by 2040. So hopefully in quite a lot of our own lifetimes, we will have a fusion prototype power plant in our country, which is really, really exciting. But there's also lots of other fusion devices across Europe and across the world. EUROfusion is the program that helps to get together all of the fusion labs across Europe. And so JET has been involved with EUROfusion for quite a long time, but there's also ITER, that big machine, that completely international one. And there's other machines in other countries too, such as W7X or Wendelstein's 7X in Germany. There's another fusion machine in Germany as well called Aztec's Upgrade. In Prague, in the Czech Republic, there's even a fusion machine called Compass, and it's currently going through a big upgrade as well. So it'll be Compass U next year, I believe. And even in Spain, there's a fusion machine called TJ2. So you can see there's lots of work going on in fusion all over the place, which is really, really exciting for everyone, I think. And it's not just governments either. It's really becoming much more involved with industry too. And so there's more and more private fusion companies starting to really make headway in fusion, which is pushing all of us. And that's a really good thing because ultimately we're going to have to all work together with public research and private industry to bring all of this technology out there to everyone and to be able to really power all of our homes in the future. And so on this slide, I just want to really bring everything together and show you that actually fusion doesn't just need the science, it needs lots of supporting technologies too. So to build these future fusion power stations, we need machines like JET and Mast Upgrade to help us learn more about the science and the engineering designs that are going to be needed to build the best possible fusion machines in the future. But we also need groups working on robotics to help us maintain and upgrade all of these machines remotely. We also need lots of work in material science as well to figure out what will be the best materials, some of which we might not have developed yet, to build fusion devices out of. And at UKAA, we're really building up a hub of these different research areas. So we have our own robotics facility called RACE, and we have our own materials group called the MRF as well. And it's not just those, but we're also looking here at UKAA and other places at how we handle the fusion fuels. Here we have a department called Heat that's looking at how to make the most of that tritium and deuterium fuel and how to best handle it. And we've even started looking at the technology that will be needed to manufacture and test all of these components in real life full scale power plants with a facility called the Fusion Technology Facility. And that's actually based up in Yorkshire, which is a brand new facility for us and really, really great new direction to be going in, showing just how fusion is going to be around the corner pretty soon. If any of you are really interested in getting to Fusion, that would be fantastic. There's lots of different ways to get involved. At UKA, we have a really good apprenticeship scheme that you can join after your GCSEs or A-levels. And there's also routes through university if you study physics, engineering, maths, or several other subjects. As you can see, we need lots of different people to help push forward all of this technology. And then after that, you could join maybe one of the big graduate schemes, or maybe even do a PhD in fusion. And then ultimately, we'd love to be able to see some of you here in future fusion jobs, either working on projects like JET or Mast Upgrade or STEP or Demo, or maybe even abroad and all over the world. There's opportunities in fusion, and they're only going to grow in the near term. If any of you want to find out more, there's loads of places that you can go. I could really recommend checking out UKAA Official on our social media, particularly our YouTube channel at the moment has lots of great resources, including a whole YouTube series we made going into more detail on some of the basics technology that you need for fusion to happen, called our Fusion Tutorial series. On the ETA website, there's a new educational resource that was just launched earlier this year called Infused. And this has a collection of lots of different resources from international partners working with fusion. There's even podcasts now on fusion. There's one called A Glass of Seawater that was made by some of the sort of PhD students that are working on these projects, and they interview all sorts of people that work in fusion. And there's also lots of books out there too. Or if you wanted to just get in touch with us directly, feel free to email the team here at UKAA with education@ukaa.uk, or you can get in touch with all of our partners across EUROfusion through emailing contact@euro-fusion.org. So with that, I hope you really, really enjoyed all of our look around the hottest place on Earth and learning much more about fusion. What I'll do is I will just leave up This last slide of the Science in Schools webinar series as just a little reminder of the next webinar that's coming up in February, all about exoplanets. And for those of you that are here live, feel free to ask any more questions that you might have in the next 10 minutes, either using the chat box or the Q&A feature. And if anyone's watching this that's watched it recorded, feel free to get in touch with us directly, or maybe leave a comment on this video wherever you're watching it. Thank you very much for joining us, and I'll now have a little look at any questions that we've got. So, I can see that we've got one question that's come through already, and I'll read out the question and then answer it. So we have someone that's asked, speaking of things to study to get into fusion, I personally planned on going for a master's in physics and then using that to build off a master's or PhD in fusion and nuclear chemistry. But I am still looking for a good university to study this stuff. Are there any universities that you over at the UKAEA recommend? Well, there's actually lots of different universities that offer opportunities in fusion. If you go and study an undergraduate degree in physics at universities across the UK or abroad, it might be that in the third or final years, that in the third or final years of your physics degree, you might have specialist modules in fusion, and they would really go into some of the sort of detail that would be needed to understand it for you to then go on to do a master's or a PhD. There's lots of universities that might offer this. Some of the ones that come to mind are York University, which has a very good Institute of Plasma Physics. I know that there are some great courses at Manchester University and Bristol University, for example, as well. What I'd really encourage you to do is just look around and try and see online and visit universities that you see have really good fusion modules, maybe in the final years of their physics degree, and if they interest you. Thanks for that question. We've got a couple of other questions that have come through in the chat box as well. So we've got one that's asked, are we going to post the recording for further distribution? Yes, the team at Science in Schools will receive this webinar recording after the event, and then they will post it up, and I'm sure they'll be able to circulate the link to all of you that have attended today. Are there any degree apprentice level apprenticeships from UK? Someone has asked. We are looking to expand our apprenticeships into degree level apprenticeships. We've already got a couple of people studying for degree level apprenticeships in engineering and some other business support degree level apprenticeships as well. So it certainly is an option if that's the sort of thing that you do. And in those degree level apprenticeships, what you would do is spend some time actually studying with a university and doing a degree alongside working on projects here at UKAEA, getting hands-on practical skills and still earning while you're getting a degree as well. So could be a really good option for some people that are interested in that route. Okay, fantastic. If anyone has any final questions, feel free to ask. I'll just wait for a moment to see if anyone's got anything that comes through. And all I can say is that unfortunately, right now, we haven't actually had any pulses happen in this last hour, but what I can recommend is do check out our YouTube channel at EIROFusion, and you can see several exciting pulses that we've put up online. And there's lots of other places where you can see other pulses from fusion experiments across the world too. So do check out all of the stuff that's available online to you. There's loads and more stuff on fusion just growing every day. We have had one more question come through as well, and the person has asked, where can I find the recording of this webinar so I can share it to some friends as family? So the people from Science in Schools will get a link to this, and I believe what they will do is put it up on their YouTube channel, which is Science in School. And I'm sure that I can ask them to try and send the link to everyone that's attended today, and then you'll be able to share that link far and wide as well. It would be really great if you've got interested friends and family or other schools that would be interested that haven't been able to attend live. Okay, with that, I think I'm going to close this webinar for today, but thank you so much for joining us. Really hope that you have enjoyed this little look around the hottest place in Earth and even enjoyed our sneaky little look inside the control room of JET, the world's biggest fusion experiment today. Thank you very much, everyone, for coming, and I hope you all have a great rest of your day. Take care.